So the outline for today is we're going to review the control of pulmonary ventilation. We'll talk about movement of oxygen and CO2 in the body. That goes 2 lectures ago, we talked about that, and I just want to make sure that pieces of that are clear with you, so I'm going to kind of move through that diagram with you guys together again. Then we'll talk about central and peripheral chemoreceptors, just generally, so that we can recap what we talked about yesterday. And then we will run an experiment together. So hopefully you guys have read the pre-lab information that kind of discusses what we will be talking about. So we'll have, actually Grant will be our subject today. So he will be, we'll be doing all different kinds of experiments on him. So we'll have him hold his breath for a little while, and then we'll look at inspired and expired O2 and CO2 levels. We'll have him, we'll extend his dead space, we'll have him hyperventilate, breathe high CO2, breathe low oxygen, and kind of see what the differences are in our body's response to these different stimuli. And I kind of want you to think about what we talked about yesterday in class and how that will apply to the experiment that we run today, and hopefully the data will kind of match. You never know, but hopefully the data will kind of match what we predict will happen. So before we do any of the experiments, I think it's important to kind of think about what's your hypothesis? What do you think is going to happen based on what you know about the physiology already? That's really the empowering part about physiology, and what I hope to teach you guys is that when you're thinking about situations, you can kind of start to piece through the physiology and start to apply that physiology. And then many times you can see if you're right, which is kind of fun. So then we'll work on CT 7.7. That's the saturation versus content piece. And so that's one of the main reasons why I want to go through this movement of oxygen and CO2 in the body really quickly again. And then at the end of class, we'll collect that CT, and then we'll also collect the extra CT as well. Okay? All right. So I'm going to start by talking a little bit so that we can get all up to speed, just kind of covering and reviewing a few things that we already talked about previously. So let's start with the movement of oxygen and CO2. So I'm going to draw this out on the document can instead. Sometimes it makes me move a little bit slower, and I feel like students appreciate that a little bit. So, all right. So I started up here with a PO2 of 160, and that's atmospheric oxygen. Okay, where does that number come from? I think it's important to think about where that number comes from. And if you think about the atmosphere as a pie, and all of the pieces of that pie added together equals 760 millimeters of mercury, that's atmospheric pressure. That's total atmospheric pressure. Okay? So total atmospheric pressure equals 760. And so if we add up all of and what is that adding up? So essentially it's adding up all of the different gases in our atmosphere together. And so each little gas that we have in our atmosphere is going to contribute to a different piece of this pie. So it turns out that oxygen is about 20% of that pie. Okay. It's a little more than 20%, but oxygen makes up about 21% of that pie, and all of the other gases kind of split the rest of that pie. So if you take 20% of 760, that is 160 millimeters of mercury. Okay? So what are the other gases that are there? The other gases that might be there are nitrogen, carbon monoxide, carbon dioxide, hydrogen. All of these different gases are going to contribute to a slice of that pie. Water vapor, that's going to be a slice of that pie. And so we can calculate their partial pressures, and that's what a partial pressure is. It's a partial of the total amount of pressure that exists in our atmosphere or within a given space. So we will talk about the partial pressure of a gas in many different spaces, in the alveoli, in the blood, in the plasma. We'll talk about it in the atmosphere. And so we can describe the partial pressure of a given gas in a space. And so for oxygen, it's 160 millimeters of mercury. All right? Okay. So here we are. Here's atmospheric pressure of oxygen. And what do we do with that air? We're gonna inhale that air in. All right? So we're going to breathe that air in. And as we breathe it in, the partial pressure of oxygen is going to fall. PO2 will go to about 100 millimeters of mercury in the alveoli itself. Okay? So why does it drop? It drops because we're adding another gas to this volume. right? And that gas is water vapor. So imagine this pie now. Now we're taking this 20%, let's say, is oxygen, and we've calculated that to be 160, but now we're adding a significant amount of another gas. So as you can imagine, the water vapor pie chart is going to increase a little bit, and that's going to cut into our pie chart now for oxygen. Okay, so oxygen levels fall a little bit, water vapor's levels rise a little bit, and so we end up with a partial pressure of around 100 millimeters of mercury. All right, so now what are we doing? So the whole point of this is to, when we draw air in, is to try and move these oxygen molecules that have made their way all the way down into the depths of the lung into the blood, right? We want to promote gas exchange between the alveoli and the blood. And so what do? We have a partial pressure of oxygen here at 100. You guys remember what the partial pressure of oxygen in the blood returning to the lung? Do you remember what that value is? Actually, this is in the venous side, so I'll mark it with a V. Partial pressure in the venous blood of O2. You think it's less than 100? Yes. Okay. Somebody say what they thought it was? 40. Thank you. All right, so the partial pressure of oxygen in the venous system is 40 millimeters of mercury. Good. Now, as you can see, this sets up a beautiful gradient for us. So we're working from 100 down to 40. So which way is oxygen going to move? Down and into the blood. Good. So now we have oxygen moving down and into the blood. All right, so we're bringing in oxygen molecules into the blood. And it's dissolving into the plasma. And so what do you think happens to the partial pressure of oxygen in the blood as oxygen begins to enter and dissolve? It's going to go up. Okay, so now the partial pressure of oxygen starts increasing. All right, and so it goes from 40 and it increases to 50. As more oxygen comes in, it increases to 60 millimeters of mercury and 70. When do you think this is going to stop? Yes, when you get to 100 millimeters of mercury. And why does it stop? It stops because there's no more gradient for oxygen to diffuse. Okay, so when this reaches, goes from 40 up to PO2, now we're in the arterial system, equals 100 millimeters of mercury. There's no longer a gradient for oxygen to move, so no more oxygen moves. Recognize, too, that if this ever became greater than the alveoli, that oxygen would diffuse back into the alveoli. All right, so this is going to equalize. And when it equalizes, now we have no net movement of oxygen molecules. Okay, so now we've done our job. We've moved oxygen into the blood. But now, what percent of oxygen is dissolved in the blood? Do you remember? 2%. Good. All right, so 2% of oxygen is dissolved in the blood. So this is your dissolved compartment, all right, right here. Okay, so only 2% is actually dissolved. So we need to put oxygen somewhere else. So where do we move it? Hemoglobin, I think that's what you said. Okay, so we move it on to hemoglobin. All right, so it's very important to recognize a couple of things. One, oxygen never moves directly from the alveolus onto hemoglobin. That doesn't happen. You have to move through the dissolved component. Okay? Number two, when oxygen exists in the dissolved component, it exerts a partial pressure. There are lots of different gases that are dissolved in your blood, and we'll talk about CO2 as another gas that's dissolved in your blood. Carbon monoxide can get dissolved in your blood, so this exerts a partial pressure. There's a partial pressure of all of the different gases in your blood. Once oxygen binds to hemoglobin, it no longer is exerting a partial pressure. Okay, so we don't talk about partial pressures of bound hemoglobin or bound oxygen. We only talk about partial pressures in the dissolved component. Right? So once oxygen is dissolved in the blood, it's going to start binding to hemoglobin. Now I'm going to bring you back to this oxygen saturation curve that I've kind of drawn here. So I haven't finished the curve yet, but here's the finished curve. Now what I want you to recognize is that this talks about percent saturation of hemoglobin. And this tells you that when the PO2 is at 100 millimeters of mercury, that our hemoglobin should be almost 100% saturated. Meaning that if there are 4 binding sites, on average, all 4 should be bound with oxygen. So look at here, we are at 100 millimeters of mercury right here. So this plasma is surrounding all of our hemoglobin molecules. So that hemoglobin is experiencing a PO2 of 100 millimeters of mercury. So how many oxygen molecules do you think should be bound to that hemoglobin? 4, about 4 on average. 98% saturated, 99% saturated. So on average, there should be about 4 oxygen molecules binding to this hemoglobin. Do you see that as the PO2 increases, as oxygen is diffusing in, this graph is describing what's happening to hemoglobin saturation. So you start at 40, which is down here, right? 40 is around here. And in the lung, as oxygen is being dumped into the plasma, hemoglobin is filling up with oxygen. Okay? So now we've loaded up a bunch of oxygen onto our hemoglobin molecule. As you can imagine, as every oxygen leaves the dissolved component and moves onto hemoglobin, what happens to the concentration of oxygen in the dissolved? It decreases, right? It drops a little bit. And so then what happens? Now we have a gradient again, 100 to whatever it is dropped to. So a little more oxygen populates the dissolved. And now a little more oxygen moves on to hemoglobin. Once all of the hemoglobin is fully saturated, then what happens is we can only put the rest in the dissolved. So we'll top off the dissolved, and then that's all the oxygen we can carry in the blood. Does that make sense? All right. So now, this oxygen that's riding on hemoglobin, along with everything that we can fit in the dissolved, moves to the tissues where we want to deliver the oxygen. Okay, remember that our tissues use oxygen to make ATP. Okay, so all of the cells in your body that are producing ATP are relying on oxygen. And so that's a lot of cells, right? We have, 37 trillion cells in our body, which is a huge number that's almost hard to even fathom. But all of those cells need oxygen. Okay, and so what we're doing is we're delivering that oxygen to those tissues. Now, in the tissue, I'm going to tell you here that the PO2 is around 40 millimeters of mercury. Okay? That matches about the delivery rate to the consumption rate. So these cells are continuously using oxygen to make ATP. So this value, if you cut off oxygen supply to the cell, this value would continue to deplete, right? And that's why your cells can die if they don't have enough oxygen. All right, so we need to continue to refill and make sure that there is enough supply of oxygen to your cells so they can continue to make ATP. So here we are. We brought our hemoglobin molecule down with us. It's fully saturated. Oh, so I forgot to write this. So this is our bound content up here. Bound content is about 98% of all of the oxygen that we carry in our blood is carried bound to hemoglobin. So if you didn't have hemoglobin, you'd only be able to carry about 2% of the normal amount of oxygen, right? Which is very little. So we really rely on hemoglobin to help us out. All right, so now we move. Here again, we are in the dissolved. We have a dissolved component, and we have our bound component. All right, so the bound has lots of O2 on it. We just left the lung. The dissolved, you just simply move from the lung to your first set of tissues where you're going to start delivering the oxygen. All right, so this should still be, the PaO2 should still be at 100 millimeters of mercury. I'll zoom in on this now. Okay. So PaO2 is still at 100 millimeters of mercury. So we have lots of oxygen that's floating around in here. Do you see how, again, we now have another gradient that's set up? So we have a gradient now from the dissolved component at 100 millimeters of mercury to the cells. All right, so oxygen can diffuse down a pressure gradient into the cells. It's exactly what we want. We want to deliver the oxygen to the cells. So as you can imagine, as oxygen moves into the cells, what happens to the oxygen concentration in this compartment? It decreases, so it starts to decrease. Okay, so as oxygen moves in, the PO2 in here starts to fall. Okay, what do you think happens to the PO2 here as oxygen moves in? Increases. Okay, but don't forget that these cells are using that oxygen. So yes, although it will increase for a little bit, they're using the oxygen, so it's going to decrease again. Okay, so basically you can think of this 40 millimeters of mercury as kind of a set value. These cells are constantly using the oxygen as it's coming in, and so this number isn't going to change very much. Okay? The only time it will change significantly is if you start exercising a lot, let's say. If your metabolism increases, if you're sick, let's say, your metabolism tends to increase. Okay? When your metabolism increases, that means you need to make more ATP than normal. That's essentially what an increase in metabolism is. All right, and so in that case, you would consume more oxygen than normal. All right, and so this number might fall because the cells are in higher demand of oxygen. So at the very onset of exercise, your cells are going to start working harder, consume more oxygen, but then there's going to be a bigger gradient for oxygen to move in, so they're going to get refilled again. All right, so recognize that this number doesn't usually go much above 40, and that it can go below 40 if you are exercising intensely. All right. So there's going to be this gradient from 100 to 40 millimeters of mercury here. So oxygen is going to diffuse in. And is there anything that's repleting this oxygen in this area of the body? Right there. What do you think? Do you think that oxygen levels are, there's something feeding into this system right here that's going to allow oxygen concentrations to go back up? Okay, what is that? Hemoglobin and bound oxygen, okay? So PO2 levels are going to go from 100, let's say, as oxygen diffuses in, all the way down to what value do you think? When will that stop? 40, okay? So it's going to continue to diffuse in until you hit 40 millimeters of mercury. All right, now I'm going to show you this graph again up here. You see on this graph, they usually show you two values, 100 and 40. Some people are like, why do they show you just those two values? Well, it turns out that the cells are usually at around 40 and the alveoli are usually at 100. All right, so recognize that at a PO2 of 40, when the blood becomes, the percent saturation becomes around 40 millimeters of mercury, see what happens to our percent saturation on hemoglobin. This is actually not as accurate as I want, but the idea is that it should go down to around 75%. Okay? So hemoglobin saturation should go down to 75%. What does that mean? That means that down here, as the blood dumps oxygen, as the dissolved component dumps oxygen, this is going to go down to 40 millimeters of mercury. When that happens, our hemoglobin says, oh, I need to start letting go of oxygen because that's what the percent saturation curve is telling me. All right. So when this hemoglobin molecule experiences a PO2 of 40, because enough oxygen is left, it starts unbinding its oxygen and releasing the oxygen into the dissolved component, which is exactly what you want it to do. All right. So some of this oxygen starts moving off of hemoglobin and moves into the dissolved component. What do you think happens to the PO2 in the dissolved component when that happens? It goes up a little bit. All right. But then if it goes up from 40 to 45, now we have a little gradient. More oxygen moves in. More hemoglobin moves, or more oxygen moves off of hemoglobin, or oxygen diffuses in. And this is kind of like pulling oxygen off of hemoglobin and moving it, funneling it from hemoglobin through the dissolved and into the cells. All right, which is exactly what you want. And so now we give our cells all the oxygen that they need. We deplete our stores of hemoglobin. We deplete the dissolved, and now we move back to the lungs. Now I'm going to ask you guys a question. This is more of a conceptual question. I want you guys to think about PaO2, okay? Sorry, this is not the A anymore, this is a B, so that's for venous blood, since we're in venous blood now. All right, but we still have our hemoglobin. Based on this curve right here, at 40 millimeters of mercury, partial pressure of oxygen, how many how many oxygen molecules should I draw on this hemoglobin? 3, good. Okay, 75% saturated. Right? So this curve tells me that at 40%, at a PO2 40, I should still have about 75% of my binding oxygen bound to hemoglobin. That means that 3 out of the 4 spots should still be holding on to oxygen. Okay, so some people, when you kind of think about this conceptually, you might think, oh, I'm dumping all of my oxygen off at the tissue. Actually, it turns out, under normal conditions, if you're just sitting here at rest, your hemoglobin isn't dropping off the majority of its oxygen. It's actually carrying it back to the lung and getting refilled. Okay, so 3 out of the 4 of these oxygens should still be bound, right? Which is good. Okay, why is that? The reason why that is because if you start exercising, we need a reserve of oxygen. So if you start exercising and the PO2 in your cells start falling, okay, let's say they fall to 20. We go back up to this curve here. If this goes to 20 during exercise, you see that we're going to start dumping off the majority of our oxygen, okay? About 50%. That should be around 50%. But the idea is that if you start exercising, now we have a reserve of oxygen still bound to our hemoglobin that we can dump off at our cells, right? And that will only happen at the cells that need it. So, as you can see, some of your cells, like your fat cells, let's say, are just hanging out. They're not very metabolically active. But let's say your muscle cells, your heart cells, those are much more metabolically active because they're working all of the time. So those cells might experience, your heart cells might experience a lower PO2, or there might be a larger gradient. So you're dumping off more oxygen into the tissues that need it the most, right? Okay. All right, so now that comes back to the lung, the hemoglobin, along with that, the dissolved component, and we refill both the dissolved and the bound, and then this circulates over and over again, okay? All right, so now what I expect that you guys can do with CO2 is follow the same path in the opposite direction for CO2. CO2 comes from your cells. It starts at about 46 millimeters of mercury. Okay. I'll give you the starting points, and what I want you guys to be able to do, I can post this picture for you guys if that's helpful. Okay. So CO2 comes from your cells in the venous blood, in the alveoli, let's say, PCO2 is about 40 millimeters of mercury. So, I'm not going to draw everything out because we talked about how CO2 is carried in the body, and it's a little bit more complicated of a diagram. That's going to be too hard for me to draw on here. CO2 can be dissolved, just like oxygen. CO2 can bind to hemoglobin, just like oxygen. And CO2, the last thing, the major way we store CO2 is converting it to bicarb within the blood. Right? Those are the three ways we carry CO2. But the first thing we have to do is dissolve it. So I want you guys to think about moving CO2 from a partial pressure of 46, and I'll tell you that in the arterial system, it's going to go to 40. So here, PCO2 is going to equal 40 millimeters of mercury. Okay? So CO2 is going to diffuse from high concentration to low concentration. Oops, sorry, I drew it over here. I'm using all of it. Okay? High concentration to low concentration into the dissolved component until the dissolved component is about 46 millimeters of mercury, and then you move that, and there's a lot of conversion that happens. Some of that ends up binding to hemoglobin in just the same way that oxygen will. So you move CO2 into the dissolved, then you move it on to hemoglobin, okay? And when it moves out of the dissolved and onto hemoglobin, a little more CO2 moves from the cells back into the dissolved component, and you kind of load up hemoglobin. You also convert a lot of that to bicarb. So as CO2 moves into the dissolved onto hemoglobin, you convert it to bicarb. That bicarb gets dumped back into the dissolved, but the CO2 is gone. So the CO2 partial pressure goes down. More CO2 can diffuse in. And so this process continues until you've loaded up all your hemoglobin, you've converted the majority to bicarb, and now you just push the rest into the dissolved. So the PCO2, in the blood at the end of the day should be around 46 millimeters of mercury. All right. Now that CO2 moves back to the lung. Okay. Moves back to the lung. And look here, there's a partial pressure difference here. So 46 to 40. So now some of the dissolved moves into the alveolus. All right. And you exhale it out. Some of the dissolved moves into the alveolus, and you exhale it out. When the PO2 here falls, then some of... Oh, I'm so sorry. Yes, sorry. Okay, so here. So now you're back in the lungs. There's a partial pressure difference from 46 to 40. Some of the PCO2 in the dissolved moves into the alveoli, and you exhale that out. Some more moves out into the alveoli, and you exhale more out. The PO2 in the the partial pressure of the dissolved starts falling. Some of the hemoglobin lets go of the CO2, moves into the dissolved, again moves out. It follows the exact same patterns that we just talked about. And this is your way of dumping off all of your CO2 into the alveoli, and you exhale all of that back out. Okay? All right, so I'm hoping that you guys should be able to follow kind of this diagram and kind of how it works. If you get lost and you want to remember what, for the partial pressure of oxygen here, I think this graph comes in handy when you think about, I definitely would study this graph and just make sure that you're familiar with that for the exam, because I think it relates a lot to kind of what we've been talking about. It gives you a good idea of what happens if partial pressures changes, what would happen to percent saturation and bound content, all right? Okay, any questions about this diagram right here? No? Okay, all right. Let's go back to, oops, this right here. Okay. All right, so we drew some stuff out. All right, now I just wanted to generally go over this pathway. All right, so these are all the different ways we can increase ventilation. Remember, you can choose to increase ventilation if you want to. You have control to change to, you have the ability to control this. If you want to breathe harder or breathe less harder, you can hyperventilate, and we'll have Grant hyperventilate today. We have central chemoreceptors and we have peripheral chemoreceptors that also modulate breathing. So our central chemoreceptors monitor CO2 only. Okay? Remember, where would an increase in CO2 come from? Where was it in that picture? Cells. Okay? So how could you get an increase in CO2 production? Increased metabolism, increased rate of needing ATP. That happens when you are exercising many times, or if you're sick. Anytime your metabolism increases, CO2 production is also going to increase. So ask yourself that question when we start going through different exercises today. Is my metabolism changing for whatever reason? That is the only way you can change CO2 in the body. You have to change metabolism. Okay? Well, I shouldn't say that. Not the only way. But that's the only way to increase CO2. Actually, I shouldn't even say that. There's two ways. One is you could hold your breath, let's say. If you hold your breath and stop exhaling out CO2, CO2 levels should rise in the body. And two is metabolism. So is there any reason why I'm not breathing enough, or I've stopped breathing, or is there damage to my alveoli such that I can't get rid of the CO2, or have I started exercising? Both of those things could contribute to an increase in CO2 within the body. All right? So CO2 activates the central chemoreceptors. Those feed into the medulla oblongata and the pons. Remember, CO2 diffuses into the brain, into the CSF, and it gets converted to hydrogen ion. And the central chemoreceptors are essentially hydrogen ion receptors, okay? So those sense hydrogen ion concentration. When there's a lot of hydrogen ion, they activate the medulla oblongata and the pons, and they activate inspiration and expiration, okay? So you breathe more. They increase ventilation. CO2, oxygen, and pH all can activate the peripheral chemoreceptors. They're sensitive to all three parameters. That's a major difference between the two. When they are activated, they activate afferent sensory neurons that go to the same part of the brain, the respiratory control center, and they will cause a change in your breathing patterns. So if CO2 levels rise, you want to get rid of that CO2, so you inhale and exhale more. And, sorry, this thing is so touchy. You get rid of that CO2. Now, this image really takes everything and brings it together, all right? So here are your central chemoreceptors in this pathway right here, and here are your peripheral chemoreceptors in this pathway right here. So I just told you that for the central chemoreceptors, if you have an increase in PCO2, okay, that can diffuse into the cerebrospinal fluid, this fluid that surrounds the brain, all right, and it gets converted to hydrogen ion. Oh, this is wrong again. Okay, so I want you guys, oops. I want you guys to put a big X across this arrow. This is an incorrect arrow in the textbook, all right? So cross that out. what I want you to highlight is circle this hydrogen ion right here. That hydrogen ion is what is activating the central chemoreceptor here. Okay? So non-CO2 is the hydrogen ion that's activating the central chemoreceptor, which then activates your respiratory control centers in the medulla oblongata and activates ventilation. Why do we want to activate ventilation in response to an increase in CO2? So that we blow off more CO2. So we exhale more CO2 leaves. We get rid of that extra CO2, so CO2 levels fall back down to normal. This poses the stimulus of an increase in CO2, an increase in CO2 here, and we go back down to normal. When the CO2 levels return back to normal, this process isn't happening as much, and so we're not stimulating our central chemoreceptors anymore. Okay? When we think about the peripheral chemoreceptors, CO2 also activates the peripheral chemoreceptors, right? And also hydrogen ion. So remember, these two things are very intimately connected. If CO2 goes up, remember, CO2 plus water goes to an intermediate called carbonic acid, which then dissociates into hydrogen ion and bicarb. So if CO2 goes up, then you end up getting more hydrogen ion. And too much hydrogen ion in the plasma, it can be a bad thing. It starts acidifying the blood, and you start denaturing proteins. Right? And so we need to get rid of some of that hydrogen ion. And so how do we do that? So we do that by stimulating the peripheral chemoreceptors that activate the sensory nerve. Remember, this is your afferent nerve that goes to the control center within the medulla. Activates ventilation. You see how if you activate ventilation, CO2 levels go down because we exhale it out. And then we shift this reaction to the left, and we produce more CO2. That hydrogen ion that was originally stimulating this receptor actually gets converted to CO2, so it's no longer hydrogen ion anymore, and the pH returns back to normal. Okay? So both CO2 and pH play an intimate role with each other. So if you just sat here right now and you started hyperventilating, you started breathing off lots and lots of CO2, what do you think happens to the hydrogen ion concentration in your blood? Yeah, it goes down. Okay, so you can go into what they call respiratory alkalosis because you breathe off too much CO2. Okay? If you hold your breath for 20 minutes, what can happen is you could acidify your blood because you're not breathing off some of that CO2, and instead it kind of gets trapped as hydrogen ion. So you can acidify the blood as well as make it more neutral, or you can actually make it more alkaline as well. Make it more basic. All right, PO2 also can stimulate the peripheral chemoreceptors. This has to fall pretty low for that to happen. Okay, so PO2 has to fall below 60 millimeters of mercury before you stimulate ventilation. Normally it's at 100. So having it fall to 60 is a difference of 40 millimeters of mercury before you start stimulating ventilation. So there has to be a pretty drastic drop in your PO2. Before that happens. But if that does happen, let's say if you start breathing, go to altitude, this could happen. This will stimulate your peripheral chemoreceptors. Again, work through this pathway to increase ventilation. You increase ventilation, and hopefully you bring more oxygen into your lungs, put more oxygen into your dissolved component. The PO2 should increase back up to 100, or hopefully back up to a normal range. You stop stimulating the peripheral chemoreceptors, and this is again classic negative feedback, where the response opposes the stimulus. Okay. All right, so what are we going to do today? There are two things that I want you guys to think about. First of all, let's start with CT 7.7 really quickly here. So if you pull out CT 7.7, if you look at this, all right, start. Does anybody have a blank one? I don't have a. Do you guys have a blank one back there? I didn't think I needed to see that. Can I use somebody's blank CT? No blank one. Thank you. Thank you. Okay. All right. I have one, but it has a lot of the answers on it, so I don't want to show you that one. Okay. All right, so what you're going to be doing today is I'm going to ask you about lots of different scenarios, all right? So PaO2, I want you to write above that. Where do you see PaO2? What compartment are we talking about? Okay, the arterial system. So I said there are two compartments within the arterial system. You either have hemoglobin or you have dissolved. Okay, so if you're exerting a partial pressure in the arterial system, that means you're in the dissolved compartment. So above that, I'll write it for you so that you're not missing out. You can write dissolved. Okay? All right. So also, when you think about changing the dissolved, remember, how does that change? I want you guys to think about how can you change and make sure you put more oxygen in the dissolved. What is one thing you can do? What do you think? Remember where this came from. Okay, so what I'm asking you is how can we change this number to be higher? This number is dependent on what value? Alveolar, okay, which is also dependent on what other parameter? Atmospheric, good. So I want you to think about, is the quality of my air that I'm breathing changing? Okay, let's say you breathe polluted air. That could change atmospheric, which could then change alveolar, which could then change dissolved, which can then affect bound. Okay, do you see how all of these are intimately connected? Okay, so quality of air. And another way you can change that is by breathing more. Okay, so is my ventilation changing? Okay, so those are the things I want you to think about when it comes to thinking about the dissolved component. All right, so PaCO2, where does CO2 come from in our body? Our cells. So what is one way that you can increase PaCO2 in our blood? Exercise, okay? Is my metabolism changing? So is there an increase in metabolism or decrease? That can change your CO2. Is my ventilation changing? That's another way you can change your CO2. Change, that triangle sign means change, ventilation. If you hold your breath, you see how CO2 will begin to accumulate in the blood. Okay, because you're not exhaling it out, so you're not allowing it to move. It's going to get stuck in the alveolus, essentially. And once you're stuck in the alveolus, then now the pressure difference between the blood and the alveolus is all the same. So basically, it gets stuck in the blood and it continues to circulate. You can't get rid of it. Okay. All right. Now, percent saturation. What is that dependent on? So percent saturation is how saturated is this hemoglobin. What do you think that's dependent on? Do you remember this graph? This tells you how saturated hemoglobin gets at different partial pressures of oxygen. Okay, so percent saturation is determined by what partial pressure of oxygen that hemoglobin is experiencing. In the alveoli, PO2 gets up to 100. So here they're showing you at 100, it should be 100% bound, or 100% saturated, sorry. At a PO2 of 40, when you get down here, it should be about 75% saturated, which is what they're showing you here. Okay, so percent saturation is dependent on PO2. Okay, which is your dissolved component. It's the same as your dissolved. All right. Now, total content, the total amount of oxygen that you can carry in your body, remember, is you add two components together, either how much oxygen you can bind, that can bind to hemoglobin, and how much you dissolve in the blood. Those are the only two places in our body where we can carry oxygen. So you add those two components together and you get total content. So now you have to think about what factors affect bound and what factors affect dissolved. And dissolved and PaO2 are the exact same thing. Okay. All right, so you're going to move through different scenarios here. And I want you to kind of think about those parameters and how they might change with those different scenarios. That will kind of help you answer some of these questions. Thank you. Okay. All right, so now we're going to actually do the experiment. So what are we going to be doing today? Everybody should have this figure. All right, so in your course packet is page 56. And here's what we're going to do. We're going to bring Grant down here, And Grant is going to be your subject. So we're going to have lots of different conditions that we're going to put them through. So if you go to page 55, it's going to describe all of the different conditions. All right. So here are the conditions that we're going to put him through. We're going to have him hold his breath for about 60 seconds. All right. I want you to think about what's happening to expired CO2 and O2. What do you think is going to happen? We're going to have him hyperventilate, which is an increase in tidal volume and an increase in respiratory rate. Right? You have to be making sure you're breathing more air in. Otherwise, this is not going to work. Okay. So what happens to expired and inspired CO2? We're going to have him breathe high CO2. We're going to have him breathe low oxygen, and we're going to look at, are there changes in ventilation that are happening? And then we're going to do an artificial extension of his dead space. Okay, and then we'll look at ventilation as well. Okay, so you guys can fill this out. I'm not collecting this, but this is something that you guys can save for yourself, for your studying. So when you're studying for the exam, it's kind of nice to have some of these values with you. All right, so here we go. Everybody say hi to Grant. And what we're going to do is we're going to start by having him just breathe kind of calmly at rest, okay? So we want to kind of just get some baseline data. Oh, sorry, that's me. I got to change, right? I always forget which button I have to hit. Oh, good. Hit the right one. Okay, so he's breathing through a mouthpiece here, and what we're going to be able to see are a few different parameters. All right, so we'll be able to see changes in flow, but you can see that flow is going to kind of be respective to air moving in and out of his mouth, so kind of similar to tidal volume. We can look at how many liters per second he's breathing in and out of his mouth, so that will be our tidal volume. What you'll see here up at the top and on the bottom are going to be changes in CO2 levels and oxygen levels. So when he breathes in here, he should start at a value of 0. He shouldn't be breathing in very much CO2 because we don't have very much CO2 in the atmosphere. So CO2 levels should be low, and when he exhales out here, CO2 levels should be higher because that CO2 is coming from his body. Right? So we're going to be monitoring inhalation, which is at the bottom, and exhalation at the top of CO2. All right. We count the number of breaths per minute. That will give us his respiratory rate. And then here down at the bottom, here we have oxygen. So we're going to have him breathe, we're going to start him at 20%, 21%, around 20-21% oxygen, which is atmospheric oxygen, right? And when he breathes out, what you'll see is it's going to drop because that oxygen hopefully will make its way into the bloodstream and we'll get rid of some of that oxygen. So the oxygen that he breathes out should be lower than the amount that he breathes in. Okay? All right, so we can start to watch some fluctuations here. Should we take kind of a baseline? Do you want to take a baseline? What values are we getting here? So this is where Grant is talking. Okay. So
let's wait to get over to the left side of the screen.
Okay. So when this kind of reaches the left side, that's going to be starting. It's a little bit easier to measure. So let's see what his.
So it looks like we have inspired low CO2 and about hard to say because the CO2 keeps changing.
Yeah. So you can see the CO2 is lower here, but then it kind of increases a little bit.
And normal rate. I'm going to call this about 6%.
Okay. That's a little bit higher than normal, but that's okay. Good. All right. So expired CO2 at rest. Let's see if we can. Here. Okay, so expired CO2 at rest is going to be 6%. Okay. Inspired CO2 should be 0, right? Is that the value we get for him for inspired? 0?
Yeah.
Okay, so 0%. Inspired O2, what is our inspired O2? 21.24, we're right on the dot, good. 21.2%. And expired O2?
Expired has gone down to 12.67, but right now, at this point, it looks like it's about 14.
All right, let's say 14. Seems a little bit more normal to me. All right. Okay. So now what we're going to do is we're going to have Grant hold his breath. All right, not for 24 minutes, but for 1 minute. Okay, and we should start to see in 1 minute changes in some of these gases. All right. So let me know when you are ready. And yeah. Okay. So deep breath in. All right, so in this minute, let's think about what do you think is going to happen when he exhales out? Which parameters do you think are going to change? You think inspired CO2 is going to change? What do you think? No? No, inspired CO2 shouldn't change. He's still breathing the same air. What about expired CO2? Do you think that's going to change? How do you think it's going to change? Up or down? It's going to go up. Good. Thank you. So expired CO2 should go up, which is hopefully what we will see. What about inspired O2? Do you think that changed? Do you think the amount of air that he inhaled for that one breath changed at all? That oxygen he's just breathing in is kind of set. So we're setting, he's hooked up to an oxygen and a CO2 system. So the oxygen, the quality of air that he's breathing in, has stayed the same. It'd be like you guys taking in a breath right now and holding your breath for a minute. All right. So inspired shouldn't change, but think about what's happening when he holds his breath. Okay, oxygen's moving from the alveolus into the blood, from the alveolus into the blood. But we're not replenishing that 100 millimeters of mercury in the alveolus anymore. That oxygen continues to deplete. So when he exhales, what do you think is going to happen to the amount of oxygen that he exhales out? Do you think it's going to increase or decrease? Decrease. It should go down a little bit because he's ended up using that oxygen and we're not replenishing it. So that oxygen kind of gets trapped. And the amount that he gets into his lungs, that's what he can feed his blood with. And so hopefully, let's see if that happens. Okay. Oh, did he exhale? Oh, sorry. Good. All right. So I already missed the fun. Okay. So what we saw here is Grant held his breath for a minute, 70 seconds. Sorry about that. And he exhaled out. So let's see. How did that change? So what value do we get for this?
That value of exhale CO2 was
Almost
almost 8.
8%. Very good. Okay, so expired CO2 went from 6% to almost 8%. All right. Inspired CO2 should stay the same, so that should be about 0%. Inspired O2, that should stay the same. Should be around 21%, 21.2%. Okay, and expired O2, what did that go to? 9.6%. Okay, so Grant, you're doing a great job. Okay, so, sorry, I forgot to take our tidal volumes. Did you, by chance, Bill, grab our tidal volumes and respiratory rate at rest?
All we can talk about on this particular graph is the flow rate.
Okay.
I always recommend that subjects just take normal tidal volume.
Yes.
Anywhere from 5 to
7.
900.
Yeah.
Sometimes depending on the amount of anticipation.
Uh-huh. But can we count breaths?
It's pretty normal. This looks like it's around 700.
So what do you think in terms of respiratory rate?
His respiratory rate has gone up a little bit now that we're using the test, but it is.
So you can see here that his respiratory rate looks a little bit higher. And do you see how it looks like it's starting to slow down here a little bit more?
These 22.
What about that? Yep. Yep. Yes, so you can count the number. Yep. Yep, you can. So each one of these is a breath, right? So we can count the number of breaths per minute. I would guess between 12 and 14. But remember, he just held his breath, so your respiratory rate is going to change in response. So, but if we count from right now, let's say he's closer to a baseline length. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to say 10 is around 30. So if we double that, that's about 20. That's actually a little bit higher. Probably because he's a little nervous. You guys are all watching him. So we'll just say our respiratory rate is around 20. Tidal volume, we don't really know. So we'll just look for changes in basically how often or how deep he is breathing. So when we have him hyperventilate, you will see how there'll be a drastic change in tidal volume that we can measure. Okay? So respiratory rate, we can start at 20. And for changes in tidal volume or ventilation at rest, those are rest values, so we're not looking for changes quite yet. So you can just put a mark next to those. So here's what mine looks like right now. Oh, wrong one. All right, we'll let Grant relax for a second. Okay, so. Okay, now, document camera. It's like 5 buttons that I can push. I pushed all of them. All right. So tidal volume at rest, we're not measuring changes yet. His respiratory rate at rest was 20, so we'll compare everything to that. He's held his breath, and what we saw when you're holding your breath is that he had no tidal volume, right? So no tidal volume, no respiratory rate, no ventilation because he's holding his breath. All right. So now what we're going to do is we're going to have him hyperventilate. Hyperventilate, again, means that you have to increase not just your respiratory rate, how many breaths you're taking per minute, but you also have to increase the depth of breathing. So you have to, I don't know what that alarm is. So you have to take in more air for every breath, all right? So, all right, so Grant's going to start hyperventilating. So see how he's taking in more air per breath and his respiratory rate is increased. Okay, so this is the onset of hyperventilation. What I want you to see right away is that as he's breathing more, the CO2 levels are starting to drop. He's breathing off more CO2. Okay, so CO2 levels start to fall because he ends up breathing more of that CO2 out. Okay, so CO2 levels are dropping. This just looks beautiful. Okay, beautiful. At the very same time, oxygen levels that he's breathing out are increasing. So he's breathing more oxygen in, and he's even going to hyperventilate even more here. So you can see an even further drop in CO2, okay, that he's exhaling out. Okay, so he's getting rid of CO2 in his blood, and the CO2 is coming out, and the oxygen levels are increasing. Okay, so the amount of oxygen that he's expiring is going back up. Very good. That is beautiful data. Okay. All right, but look, the inspired CO2 is staying at 0, and the inspired oxygen is still staying at 21%. So that's still staying pretty constant, but the amount that he exhales out has gone way down. Okay. Or sorry, for oxygen has gone way up. So normally he breathes out about, looks like around 15%. Now he's exhaling out around 19, 18% here. Okay. As you can see, this is beautiful. So when he starts hyperventilating here, you see that initial drop. If he hyperventilates even more, you see a further drop, which is just exactly what you want to see. And that's depicted both here and here. Okay? Further drop. And a further increase here in oxygen that he's exhaling out. Okay, so now we're going to have him go back to normal breathing, just normal tidal volumes. So let's see. So for CO2, I bet CO2, let's say, fell from here. Oh, it's so hard to say because it's in the middle. Let's say it fell to about 2.8%. Okay? So let's say he went from expired CO2 went from 6 down to 2.8%. Inspired O2 went from, let's see where he's at right now. Looks like when he inspires, inspired is still going to be at 21%, but expired went from, let's say, 18% that he exhaled out to about 19.5%. So let's just say 19.5%. All right. Inspired should still be 0 for CO2, and inspired O2 should still be 21%. Okay. All right. Okay, so next what we're going to do is we are going to, so tidal volume. So tidal volume increased, obviously. So it increases tidal volume, increases depth of breathing, increases tidal volume. So that went up. So you can put an up arrow for that. Respiratory rate also went up. So you can see here, here's a respiratory rate. This is even still faster. Before we had a respiratory rate of 20. Now within, 20 seconds, I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. He had about the same amount of breaths per minute in 10 seconds as he did in 30 seconds. So his respiratory rate went up significantly. Okay, so respiratory rate went up significantly because he was increased not only his tidal volume, but also his respiratory rate. His ventilation definitely went up. Remember, those are the 2 factors that contribute to ventilation. Okay, so here's what I got so far. Increase in tidal volume, increase in respiratory rate, increase in ventilation. That's exactly what we saw. Inspired CO2 still stayed the same. Expired CO2 dropped to 2.8. Okay, so we ended up actually getting rid of a lot of that CO2. Now, not as much CO2 is coming out for every breath. Okay? And so he's breathing more. So for every breath, he's bringing out more CO2. Okay. Inspired O2 should be the same, 21%, still the same. And expired O2, he's now kind of fully saturated his alveoli. He's breathing, so more oxygen comes up. It's not being depleted quite as rapidly because he's repleting his alveoli faster than it's getting sucked out of the alveoli. Okay, so you get an increase in expired compared to baseline, 14 to 19.5. All right, so now what we're going to have him do is we're going to have him breathe a high concentration of CO2. All right, I think it's a 5% mixture of CO2. Yes, so 5%. Yes, 5% CO2 and 95% oxygen. Okay, so what we have here is a kind of an old school spirometer. This is the way they used to do lung volume tests back in the day. So what we've done here is fill this cell with a mixture of 95% oxygen and 5%, or 95% oxygen and 5% CO2. Why do we do that? I want you guys to recognize that we're keeping oxygen levels high, but we're manipulating CO2. Okay? So we want to see what happens when just CO2 levels increase. What happens when we just breathe in a high mixture of CO2? What do you guys think happens here?
I'll just ask how, low is the pressure of CO2 normally?
In the atmosphere?
Yeah.
0.3 millimeters of mercury.
Okay.
So it's very low. So this is a significant amount of CO2 that you're breathing in. Okay. So what do you think is going to happen to his ventilation when as he breathes more CO2 in? It will increase. Okay. Good. So CO2 should make its way into the lung eventually. So it goes into the alveoli, gets into the blood. In the blood, PCO2 levels should start to go up. And remember, PCO2, small changes in PCO2 should powerfully activate ventilation. Through which set of chemoreceptors? Central or peripheral? Both. Okay. Which is, you kind of have 2 ways of detecting CO2 changes. All right. And so when we increase this PCO2, we should expect to see an increase in ventilation. All right. What is the body trying to do? The body's trying to get rid of that CO2 by breathing more. Right. But it's not going to help him because he's breathing a higher percentage of CO2. So the more he breathes, the more CO2 he's going to breathe in. Okay. All right. Oxygen levels should not be changing in this case, or they might change a little bit as we consume some of the oxygen. So we'll see an initial drop in the oxygen as he's using that oxygen, which we will see. But CO2 levels should continue to increase. All right. Okay. Let me know when you're ready. Oh, so when he breathes in, what you will see is this little valve will drop. So this little valve, if he breathes in through this mouthpiece, this will drop down, and the oxygen will, or the gases will move into his mouth through here, and then when he expires, that gas will move back in. Okay, so you'll see this thing kind of go up and down, mirroring his breathing. So if you start to see this thing go up and down more, that means the respiratory rate is increased. You may or may not be able to see that, but you should be able to see it reflected here when we measure the rate and the flow of gases moving in and out of his body. Okay? All right, good. We're ready. I will switch back. Yes, here we go. All right. Okay, so first of all, I want you to notice that we've changed the axes here. Okay, so before we started at, we were at 21% oxygen. Because we're going to have him breathe 95% oxygen, this is going to go way up. All right, so our baseline for inspiration is going to go up to 95% oxygen initially. And you will see that. The CO2 hasn't changed. Okay, so CO2 still, inspiration is still 0. He's still breathing out about 6% CO2, okay, which is kind of what we saw at the beginning, right? Yeah. Flow rate looks relatively normal, okay? Breathing in and out, all right? So what we want to see is an increase in respiratory rate once he starts breathing in that high CO2 mixture, okay? All right, let's see if that happens. You can see him as he breathes in, the bell goes down. As he exhales out, the bell goes back down. Okay? All right, so now you can see he's breathing a high mixture of oxygen here. So oxygen starts high, drops down low, inspired and expired. So his expired goes up to about 50%. This should level off. You see here that he's starting to breathe in a much higher percent of CO2, so that's working. The CO2 levels are increasing even more. And what we should see is that CO2 levels should start to rise over time. And look at what's happening to ventilation here, even right away. Okay, so ventilation is starting to breathe more deeply. All right, so our ventilation response is already in place. So do you see how this is increasing even more? So now he's starting to take even deeper breaths. So he's firing those respiratory centers within, or the respiratory centers within the brain to increase ventilation, increase contraction of the diaphragm, increase contraction of intercostal muscles so that you can take more air in. Okay, so look at the difference here. This is due to your central chemoreceptors firing right away. That's how fast they start firing. All right, they're going to start sensing small changes in CO2 right away. So this is a beautiful response. We've kind of started to see slow increase in CO2 accumulation. We've seen, it looks like oxygen levels started to level out. You can see right here, directly compare this tidal volume compared to this tidal volume, there's a huge difference, okay? So his breathing, his depth of breathing has increased significantly. If his depth of breathing is increased, that means his ventilation is increasing significantly as well, all right? Okay. I think we should be good with this. I don't want you to feel like you have to keep breathing a high percentage of CO2. Okay, good. That looks really nice. That looks really nice. So you can even see here that the difference that the CO2 levels have continued to increase even more. So, Bill, whenever you get a chance, we can get some measurements. Once he puts that back, we'll get a couple measurements here. I'll go back to the document camera, but that was a beautiful response. That was gorgeous. Okay, so as you can see back on the screen, since tidal volumes come back down to normal, CO2 levels are starting to drop back down to normal again as breathing is normalized and as he's not breathing in that high percentage of CO2. Oxygen concentrations are falling back down to normal as well. Okay, so during, for the inspired CO2, his inspired CO2 should be around 5%. All right. Inspired O2 was around 95% initially. Okay, it kind of dropped down a little bit as we consume some of that oxygen in the bell. So every time you take a breath, you pull some of that oxygen out, and then that oxygen, the total amount goes down a little bit. So we saw a little bit of a drop in oxygen there. Okay. Wait for Bill, and then he can give us some actual measurements for these values here. Looks like to me that CO2 went up to about 7.5% here. What would you say CO2 was at the end for expired?
The CO2 expired was 7 3/4.
Okay, 7.75%. Okay, what about expired O2?
Expired O2 was about 70. Expired O2 would have been, I'm going to call that 73.
Okay, 73. Okay, so do you think his tidal volume increased? Yes, it definitely did. Okay, so you definitely saw an increase in CO2. Did his respiratory rate change? I think that his respiratory rate might have even gone down a little bit because he was taking such deep breaths, it looks like. If you look here, his respiratory rate now is kind of has sped up a little bit. But I don't know what his respiratory rate was right before. But here, let's just say 30 seconds, 1, 2, 3, 4, 5, 6 breaths. So his respiratory rate definitely, that's about 12 breaths a minute. So his respiratory rate went down a little bit. As you can see, the depth of breathing, he was taking in more air. So I think his ventilation was increasing, because that's what we would expect. But it's increasing because he was taking in more air. So his ventilation, his tidal volume was compensating more for the respiratory rate in terms of the increase in ventilation. So his respiratory rate actually dropped a little bit, but his ventilation I still think went up because this tidal volume went up so much. Okay. Does that make sense? Okay. All right, so now we're going to see if he breathes a low O2 gas mixture. And we have a CO2 absorber. So what that means in here is that as he exhales out CO2, that absorber is going to absorb that CO2. So when he breathes back in, he's not going to be breathing in the same CO2 he just exhaled. Okay. So in this case, CO2 levels should remain low for inspired, and O2 levels are going to also remain low. And what we should see, so what do you think? Depends how low the oxygen is, right? So we'll see. If the oxygen levels are very, very low, what do you think is going to happen to respiration? It should increase, right? Through which set of receptors? Peripheral chemoreceptors, okay? What if oxygen levels are low, but they're still above that 60 millimeters of mercury? Do you think we're going to see a ventilation response? No, we probably won't, okay? So let's kind of see what happens. I don't know what the O2 mixture for this is. So let's see if we get a ventilation response, and that should give us an idea of where his PO2 is. So we'll have him breathe for a couple of minutes. This oxygen, we'll see what it is when he starts breathing it, actually. Let's see. All right, so what is our inspired O2? Or I guess when he hooks up to the valve, we'll see what his inspired and expired O2 are. All right?
Expired O2 is going to be around 22%, 21 something, and the expired right now is going down to, it's going down to about 14.5.
Okay, so these are our baseline measurements, right? So this is at rest. So we haven't hooked him up to the bell yet to breathe that low O2, but that matches pretty well what we got right in the beginning. Okay, so his inspired is still 21.2. His expired is around 14, which is what he was at the beginning. Looks like CO2 levels are still around 5, maybe just a hair above 5. 5.5%. Okay, which matches again what we got at rest. So these data look pretty good. All right. So, all right, I think we're ready to hook them up.
All right, well,
So he's going to start breathing. Remember, a mixture of low oxygen, so we should start to see the oxygen drop. Okay, so you can see that the oxygen concentration here, see when he breathes in, is dropping. So it started around 15 or 16, now it's dropping 14 down to partial pressure, or 21%. Started at 21%, now it's down to 12. Okay, so you can see this is continuing to drop. Inspired, okay, sorry, inspired we started at 20, okay, and it's moved down to 19, 18. kind of fluctuating here a little bit. But expired is continuing to drop.
Scrubber is about 7 quarters CO2.
Okay, so CO2 is about 7.25. So that's for expired. Okay, inspired oxygen is falling between, looks like it's about 16, 17%. What would you say for inspired?
Expired is about 9% right now, and 8% will come off.
Okay, so that's expired. Okay, so at 8%, we're going to come off. So that's less than half the normal amount of oxygen that that we would expect. So, yep. Okay, so what do you think is happening here? Do you think that there's a change between here and here in terms of ventilation? What would you say? Yeah, it should be increasing. That's what we're seeing here. So as oxygen is falling in his alveoli, as that concentration, that means that the amount that's getting into the dissolved is falling. So the PO2 in the dissolved is falling. Good job, Grant. And so his respiratory rate is increasing. It really looks like it kind of starts to increase more around this area. So as O2 levels start to plummet, so really to me it looks more like the stimulus for ventilation is really happening in this area. So that tells me that PO2 in this area is starting to fall below 60 millimeters of mercury because we're getting kind of a much larger stimulus for ventilation here. Okay, so now when you look at him going back to normal, it looks like his respiratory rate is still elevated a little bit, but his depth of breathing is definitely not as deep as it was here. So it looks like this is kind of the peak of ventilation. So what he's trying to do here is activate those chemoreceptors, those peripheral chemoreceptors, to get him to breathe more, deeply in response to a low O2, and hopefully breathe more oxygen in to restore oxygen levels. Right? So what was the lowest that the PO2 went for expired?
CO2?
PO2. Oh, yeah, oxygen. Sorry.
I'm going to go ahead and pause this. I think we're back to the baseline.
Okay.
And I think the lowest CO2 expired was expired CO2 was basically sitting around 7.25.
All right.
Due to the scrubber,
Oh, so CO2?
the CO2.
Okay, so inspired CO2 is about 7.25.
Right. And then expired, well, that was the inspired, and there's a little bit of fluctuation in what the CO2 was. If you look right over here,
Mm-hmm. Yes.
so I can't interpret that. I think it's maybe a movement of the mouthpiece.
Uh-huh.
That O2, however, dropped below 8%. As you
Okay.
can see here, we're bottomed out.
Yep.
I'm suspecting that just looking at the curve over here, and then looking at where it's down here, that we're looking at about 6, 7, maybe 6.5%.
Okay, so for expired, it was 6.5%, let's say.
Which is
And inspired, what would you say? Looks like it dropped down to 11.
right here, here's the inspired down to 12.
Okay.
Here, I'm going to call this about 12%.
Okay, so we'll say 12. All right, so here are the values that I wrote down. Okay, so for inspired CO2, he's still was inspiring almost no CO2. He was expiring a higher amount of CO2. Actually, a little bit higher. It's about normal, okay, from what he was doing before. His inspired O2 went down significantly from 21% down to 12%, and his expired O2 went down from 14 to 6.5. So he was inspiring a much lower percentage at the peak. Kind of the lowest amount of oxygen that he was taking in was only 12% oxygen. Okay, so that's pretty significant. I'm just going to calculate how many millimeters of mercury that is. So that's about 91 millimeters of mercury. So if he's normally at 160, he went down to 91 millimeters of mercury. Now, if you were to go to altitude, if you were to go to Everest right now, the PO2 is about 28 millimeters of mercury in the atmosphere. So we went from 160 that you're breathing here. He breathed 91 millimeters of mercury. If you go to altitude on the top of Everest, it's only 28 millimeters of mercury. So that's the difference in the amount of oxygen that we can breathe. That's why if you were at altitude, if you were at on Everest, you'd be breathing 28 millimeters of mercury in the atmosphere of oxygen for the partial pressure, which is why most people have. That's why you have to have oxygen masks, because that's just not enough air to properly supply your blood with enough oxygen for you to survive. Okay. Okay. So let's see. So for tidal volume, do you think his tidal volume increased at the peak? I would say yes, it did. So I think we definitely stimulated his peripheral chemoreceptors. His respiratory rate looks like it actually stayed pretty similar. So if you look here, it looks like his respiratory rate was still pretty high kind of throughout. If we look at the differences between here and here, his depth of breathing looked really deep, but I would say his respiratory rate looked pretty steady. So I would say there's no real change in respiratory rate, but we did have a large increase in ventilation due to a large increase in our tidal volume. Okay? Good. I think this data looks great. Great 7 looks. Okay, so now for the last one, what we're going to do is we're going to extend his dead space. So basically, we're just going to put a large scuba or a snorkel on him. Okay. So this is a 5-liter snorkel. Okay, or you can kind of think about this as like a giraffe's neck, right? But the difference between a giraffe's neck and their trachea compared to ours is that theirs is much more narrow. Okay, so they even have a more narrow trachea than we do, which is kind of crazy. But that's the way that they can limit their dead space. That's the way that they can bring in air into their lungs. Otherwise, they wouldn't be able to. If they were breathing through a tube that was that size, their dead space would be just so large, they wouldn't be able to pull enough air all the way down to their alveoli. So they compensate by having a very narrow airway, but they have very, very high resistance. So they have to take long, deep, slow breaths. Their tidal volume is really, really large to try and pull air slowly all the way down to the depths of their lungs. So we're going to extend his dead space. And let's see how these blood gas changes, or the changes, what these changes look like. So what do you think is going to happen to his alveolar ventilation when we extend the dead space? Yeah, should go down, right? Because he's not able to pull air all the way from the atmosphere through that entire tube all the way down into his dead space. So alveolar ventilation should go down. Okay, and then, so what do you think is going to happen to his oxygen levels in his blood? Down. They should also go down, right? And so PO2 in his blood should start to fall. What do you think is going to happen to CO2? Do you think that he's going to get rid of as much CO2? No, so CO2 levels should start to rise. So in this scenario, we're actually artificially increasing both CO2 and we're decreasing PO2. So what do you think is going to happen to activation of our chemoreceptors? Yeah, we're definitely going to be activating our chemoreceptors because both CO2 should activate our centrals, CO2 should activate our peripherals, and the drop in O2 should also activate our peripherals. So our chemoreceptors are going to be firing, and so hopefully we'll see a response in ventilation as a result. Okay. All right. So he's going to hook this tube up. We're going to extend his dead space. And let's kind of see what's going to happen here.
So the baseline was about expired CO2 was about 6.8.
Okay, that looks normal.
Expired O2 was about 14.8.
Okay, he went up just a little bit from baseline. Okay. All right, so as you can see, inspired O2 is starting to drop because he can't pull that oxygen all the way in. All right, so inspired O2 is starting to drop. Expired O2, the amount that he's breathing out is also dropping. Okay, it looks like he's starting to breathe in a little bit more here, for whatever reason. His tidal volume, as you can see, is rapidly starting to increase. So he's taking in more air. Depth of breathing is increasing. You can see that CO2 levels, expired CO2 is starting to rise. So he's not able to get rid of that CO2 because it's accumulating in that tube. So CO2 levels are starting to go up. Oxygen levels are also, at the very same time, starting to go down. You can see a drastic increase in depth of breathing here right away. And this is continuing to starting to increase. So this looks like it's still increasing his depth of breathing as he breathes through this tube. So this is exactly the response that we wanted to see. Right? It looks like almost like his respiratory rate slowed down just a little bit here, but his depth of breathing is increasing even more. And we can see that if you compare this initial breath here to this breath here, you can see that these are long, slow inhales and exhales. So he's taking in a lot more air. So let's compare this to here, direct comparison. You can see that there's a huge difference. His respiratory rate looks like it has slowed down a little bit, but you can see that the amount of air that he's taking in and out per breath has increased significantly. Okay, so let's take some values. What do you think for CO2, Bill?
CO2 expired has gone up to about 8.
8%, okay. What about O2?
Expired O2 has dropped to about
8%, okay.
below 8 now, about 7.8.
Okay, so less than 8. Inspired O2, still, let's say it was
Expired O2
kind of fluctuating.
I don't know why it's fluctuating, but I'm going to call it at about 14.
Okay, so 14. And inspired CO2, it should have increased.
CO2 should be 0, but it's not. It's no. Take that back. It's
Should be
5%.
higher. Yeah, 5%. So he's breathing about 5% CO2 right now. All right, so we can take it off. Good job. That was really tough. Okay, so even before we saw an increase in tidal volume or an increase in depth of breathing, look at what it was at the very end. So you can see that he's taking very deep breaths here, trying to compensate for the change in the blood gas. How do you feel? You feel okay?
Yeah, better now.
Okay, good. All right, everybody give Grant a hand. That's actually really tough to do, so thank you so much.
How do you experience these 3 parameters?
Yeah, so how do you feel like your experience was for the 3? Which was the hardest?
Hyperventilating was the hardest.
Really?
The second was dead space.
Dead
And then
space?
the third was below 2, I think.
Okay. Could you feel yourself, like the respiratory rate changing? Or your depth of breathing changing? Or did you not really notice?
It would be like, oh, I feel kind of weird. I should probably breathe a little deeper. Or
Okay.
I should breathe a little faster. I end up doing that.
Okay. So a lot of times though, too, people, if you weren't in an experimental setting, you weren't watching, yourself on screen, you might not notice that you're starting to breathe more, breathe deeply, and maybe you stop thinking about it after the experiment ended, and you continue to breathe deeper and deeper, or your breathing continue to stay pretty deep, because you can see even at the end of the experiment, because we took you off here, but your depth of breathing was still pretty deep here, so that's probably totally subconscious. You're not thinking about that, but it's still happening. And that's your body's compensating for the gases that you're taking in. Okay, so let's go back to the document camera. Thank you so much, Grant. That was great. Your data was perfect. Thank you. Okay, so the extended dead space. We saw an increase in tidal volume, definitely. That was actually, I think that was the largest increase in tidal volume that we saw. His respiratory rate, because he was taking such deep breaths, I think fell just a teeny tiny bit in comparison to the beginning. But ventilation, I would say, definitely went up significantly due to such a drastic increase in his tidal volume. And his inspired CO2 went from 0 to about 5. Remember that CO2 is now accumulating in that tube, and so basically he starts rebreathing the CO2 that he just exhaled back out. All right. Expired CO2 went up to around 8%. Inspired O2 was about 14% to begin with, and then dropped down to 8% when he expired it back out. Okay. So these values all look really great. We can talk a little bit about these applications. So, okay, I was going to close the door. All right. So carbon monoxide poisoning. When you breathe in carbon monoxide, I want you guys to recognize that carbon monoxide can bind to the exact same spots on hemoglobin. I'm going to put this picture back up, as oxygen. So, carbon monoxide, when you bring carbon monoxide into your lungs, CO is another gas. So another gas gets brought into your lungs. It moves from the alveoli down a pressure gradient. Any CO2 in the lungs, there's the amount of CO, any CO in the lungs, carbon monoxide, the amount of CO in your blood should be 0. You should not have carbon monoxide in your blood. All right. So if you bring CO into your lungs, it should be able to diffuse into your blood pretty easily. All right. So once it's dissolved in your blood, it can start binding to hemoglobin. Turns out, if you have 200 molecules of oxygen in your dissolved, you only have 1 molecule of CO in your blood. That CO is going to bind to hemoglobin with preference over all of those other oxygen molecules. Okay? So it's going to outcompete your oxygen every time. So as that CO moves into the dissolved, it starts binding to your hemoglobin. Now the CO leaves the dissolved component. Now if you're continuing to breathe that CO, more moves in, more starts binding. You see then how once all of your hemoglobin are bound to CO, now there's no more room for oxygen to bind. So oxygen, you have no way of carrying oxygen. It's essentially like not having hemoglobin at all, because all of the spots are occupied by carbon monoxide rather than carbon dioxide. And that's why CO is so deadly. First of all, 2 reasons. Number 1, because our oxygen carrying capacity goes way down. And number 2, because we don't have a sensor in our body that detects carbon monoxide. There's no receptor in our body that binds carbon monoxide and tells our brain, oh, we have carbon monoxide bound. We need to get to an area where we have either we need to stop breathing the carbon monoxide or go to an area that has more oxygen around, or breathe 100% oxygen. We just don't have that stimulus in our body to recognize carbon monoxide when it's in our blood. So what do we do in that case? So a lot of times people will end up dying because, or they'll notice that their pets are also sick, but people will feel like they're sick, they have the flu, they won't feel good, but their ventilation is not changing. Okay? Why isn't their ventilation changing? It's not changing because the amount of CO2 and the amount of O2 that's dissolved in the blood should be relatively normal. If you're not breathing, through the exhaust pipe on your car, that way then CO2 might go way up and oxygen might go way down. Okay? But if you're breathing normal air with a slow leak because your furnace is leaking carbon monoxide, the amount of air that you're taking in should look relatively normal with a little bit of carbon monoxide added to it. So that means that the amount of air that you draw into your lungs and your alveoli should look relatively normal, but just have a little bit of carbon monoxide added to it, which means that your PaO2 should look relatively normal, but it has a little bit of CO added to it. Okay? So PaO2 is not changing. Your cells aren't producing any more CO2 because you're not doing any more exercise or your metabolism isn't changing in any way. So your CO is also not changing. And so if those 2 parameters aren't changing, and your pH isn't changing because CO is not changing. So if those parameters aren't changing, you're not going to activate your chemoreceptors, so you're not going to change ventilation. So people with carbon monoxide poisoning have very normal ventilation, but all of those other parameters, but their CO levels are increasing and their oxygen carrying capacity is way down. Okay, they're not able to carry the oxygen. All right, we talked about hyperventilating before underwater swimming. Decompression of an airline cabin. So when that happens in a plane, that can happen because you have a slow leak. If that happens, essentially it's like going to altitude. Now all of a sudden you're experiencing pressure at 40,000 feet. That's like being at the top of Everest. Actually, it's much higher. So the partial pressure of oxygen at that altitude goes way down, below 28 millimeters of mercury. And if that happens, then think about the amount of oxygen that you can bring into your lungs. It goes way down. And if that happens, then your dissolved goes way down. If that happens, then your bound goes way down. All right, so all of these things are all interconnected. All right. So if you're snorkeling, this is what number 4 is essentially asking you about. Difficulties breathing if you're breathing through a tube or you're snorkeling. The resistance to airflow might go up if your snorkel is pretty small. Okay? And you're increasing your dead space. So you actually have to take a deeper tidal volume to bring the same amount of air into your lungs. And I don't think we need to talk about number 5 because I won't talk about that on the exam. Okay. So from here, let's start working on CT 7.7. And it looks like you guys have about 25 minutes to work on that. So you can work on it in here if you want. And then what the TAs will do is they'll kind of circle around. When you're done, you can turn in CT 7.7. And what we will do is I'll tell you at the end at 11 which CT that you need to turn in. If you have questions, we'll circulate. We'll answer questions for you. But yeah, start to work on CT 7.7, and I think you guys should have enough time. But use this diagram. This diagram will help you kind of piece through and work through these different pieces.
Open up invitation for visual people to step into the side room. I can kind of draw a diagram.
Sure.
If that's something.
Yeah. I mean, if that's fine with me. If you want to.
Time and like.
Well, I'm wondering if you draw diagrams, if you look at the time for all the things together. Do you know what I mean?
Yeah.
But if you have, I mean, I don't know what you think. You have a half hour.
I think I'm good. Okay, I'm free time. Yeah, I'll start drawing around.
Okay. Some people, Molly's going to go into the second room. If some people want to go in there with her, work through some of this diagram in there, you're more than welcome to do that as well. Kind of break people up. If you want to stay in here, you're more than welcome. We can circulate in here and kind of talk to people and move through as well. Yes. Okay, so anemia you can think of as a low red blood cell count. Okay, all we want you to know is that your hemoglobin and in your red blood cells are working just fine, but you just have less red blood cells.
Should we like draw something on the board on
Yes, I will draw. I'll draw that on the board
Okay.
right now. Yes, thank you.
I don't know that saturated.
All right, for all of the boxes that I've shown you here, all of these boxes that you need to fill out, once with the X, I want you just to write just a little bit about your thought process, about why you think they will increase or decrease, okay? So if let's say, this is percent saturation, this is PaO2, PaCO2, SaO2, bound, dissolved, and this is EPO, and all of the different conditions, okay? So what I want you to do is just write, okay, if you have EPO, if you're giving EPO, which is something that stimulates red blood cell production, yes?
When you're talking about bound, are you talking about like the percent bound, or are you talking about the overall like quantity?
So the overall quantity that is bound, yes, to hemoglobin. But I just want one little sentence about what you're thinking, that's all. Yes?
Just asked with the 30 seconds hyperventilation for your PaCO2, if that would stay the same or decrease, because like technically when you're hyperventilating, when you're increasing ventilation, CO2 would go down to CO2 as well. But then she was also pointing out the fact that when you're hyperventilating, it's not like I'm exercising, like CO2 comes from you.
Yes, so CO2 production isn't changing.
Is it changing?
But you're breathing off more CO2, so the levels in your blood are going to start falling.
Okay.
Why do you say that? I haven't looked at that.
I'm looking at the details.
Yeah, I think that's wrong. Yeah. Yeah. But I thought the data was good. Leah's doing at 3:35. I have to look at the list. I think it's
Okay, we're good.
Yes. Oh, sorry, Tim.
Just wanted to make sure. Yesterday we said that it's okay if they say this increases.
Yeah, so if they say that, yeah, then I would say that this increases. So, but if they say that, if they say that it doesn't increase, then I would want them to say that that's why. They could have either one here. And I'm okay with both, as long as they justify what they are. So if they say, oh, this increase is less, so this might increase it. Or if they say there's no real change because that makes sense. Either one of those.
Okay, just wanted to make sure.
Now, there's no.
It's like a really simple. Like it's just like
Yeah, that's right. Just like
no,
that would be like a lot.
well, this is gonna get
Oh no, I drew on this.
Would it go up? CO2,
I think if you consider those healthy breathing, breathing on It's the reverse of the prior.
No, but it says it's like
Yeah, so now if I I'm gonna ask you about those.
and then the content was like actually this is the sound and just oh well
Yeah, so it's just dissolved. Oh, you see it dissolved. I don't think it's really a so if we increase it down to this is like what point are we at?
so it would increase that would
Just make sure that the ones that I sent you When you
That's why I'm just kind of. Oh, yeah. Or RBCs too.
And then for results.
Yeah. I'm sure
you do. Yeah.
so the results also. But I'm told that the dissolve stays the same. The 60 seconds we're not changing. What's the point? Like, and then. It's not because I'm so excited about
Because like it makes sense. But I think that when you're breathing, you're kind of your alveolar part of the oxygen. It's not static, right? Because like when you breathe in, there's more oxygen. When you breathe out, there's more oxygen. So like because you're saturated, it's going down. It's the arterial. That's like kind of how I think. Yeah. So like you can almost think of the arterial. That's like an average of your and so if that increases, then you'll be able to truly get the saturation of and then for the CO2, since you're breathing, you're also on the smile. And then when you're exhaling, you're taking the CO2 out. Venus, so Venus, okay. And then would be the yeah, so that's exactly PaCO2. Even though I said like you don't pick up any CO2, it doesn't just so I can work on it. Yeah. So yeah. I think and that's because you increasing your so like PaO2. So it wouldn't be as fun. So it's like the same argument that the PaO2 back to like there's decreasing the I don't know if this means which you might be thinking about you might be also like 200 times courtesy. Yeah. So it's like the same argument as the alcohol is 100%. Yeah. This is talking about and then it's important not to mix that with like your systemic ACO2. It's like that much is just determined by, and it's not asked on this work people. That much is just determined by your metabolism. Oh yeah. So this is why, like, I think when Dr. O's kind of going over, he said PCO2 is only determined by metabolism, but these still have to influence your pH, your arterial. So I think you guys have that concept. Well, if you have any other questions.
Oh, maybe that. Yes. Poisoning. No, oh no, carbon. Oh yeah. Like these two and so what is it? Okay, let's just yes, it was
what is this?
I mean, I'm with you. I think oh yeah, I'm just scared.
Okay, so So what's that?
Oh.
That's what I'd be asking.
What do you think? You just read it out. Well, since this is already since this is already like 98%, that's why So this situation is nothing that affects you. And then it would increase the
Okay, so the extra CT is going to be 67.6. So you're just going to rip up this one single page and going to turn in both are going to be turned in. So when you're done, you can turn that in. Oh, sorry, it's fine. I thought you printed
this is all that.
Yeah, I know. I'll see you tomorrow. I do.
And so then, since it's only a small it's like oh my goodness. Yeah, I haven't yeah, so
You? Yeah.
it's
I mean, yeah, like,
Got you a question.
I do have a question. Physics. So, I thought the whole concept was there to content.
So yes, how many changes are there? Okay, so
I thought the
okay.
two was
Oh, the percentage, the 50%. Yes. Okay, breathing it back. So yeah, but let's say 2% of a larger number is still like.
Oh, yeah, okay, I got you. So that's the percentage, overall percentage.
Yes, the overall compared to that. Yes. So, alright. So resolve.
That's what all the time.
So, you're going to
Yeah, Michaela.
Maybe you just take it.
Yeah.
Just like last time. Or maybe you weren't missing out one day before. Were you here?
Yeah, I was actually.
Oh,
I was
okay.
that's when I said it was different.
Yeah, the 4 people were gone. Thank you.
I really just but it's actually
Yeah, it's just like,
So then, I feel like if I was like join him more play through.
yeah.
oh, yeah. I would have been able to eat it, but yeah.
I feel like if I was sick, I should still
Okay, yes,
Technically 11, but you're good. It's fine. You learned it enough. Are you not?
No, I'm not. I'm still ready for that.
Yeah. Good thing you did it.
It's a lot of work.
Kind of interesting, but not really. It's like,
Yeah. Yeah. I thought it'd be really pretty interesting though.
yeah.
Oh, really?
Or,
Oh, wow.
yeah. I mean, like I'm writing. So online sub-items is actually fun. Oh, really? Yeah, then do it. Sub-items good online. I did not.
If you multiply these two.
That sub-items burgers would be it. Burgers. It's very, like, it might be too much. It is. It's not just like the one I was doing.
Okay.
It's just straightforward. Like, when you just yeah, it felt like a 2000 high school.
Okay.
Yeah.
Then I have to go in my mind.
Yeah, that's what I was. I just want to.
But are there any other good like signing
So by all I don't know what class you can join.
I've taken course. I've taken biology in my mind. I took that. That's what I thought. And we like have microbiology. Oh, yeah. Let me know. But she was like, good. Yeah.
And if you've taken all of those, I feel like
Actually,
yeah, same.
yes. How do you call your mom? Let me know that you're cutting, and then I can. Yeah, like it's like really. So for the grading, I'll go to the grade. We're just saying, okay. Yeah.
Very straightforward.
Oh, yeah. And then.
Yeah. Since there's 4 of them.
Yeah.